Welcome to This Explainer. Today, we're stepping right into the beating heart of the modern analytical laboratory to unpack a truly fascinating process: trace element analysis in the food matrix. We're going to be looking at the precise physical chemistry principles, the daily operations, and the absolutely critical troubleshooting required for ICP-OES and ICP-MS instruments. You see, the work done here is incredibly meticulous, and understanding these foundations reveals exactly how we guarantee the safety of the food on our plates. Let's get started. Here's our roadmap for today. First, breaking down the matrix. Second, igniting the plasma engine. Third, measuring light and mass. Fourth, calibration for precision. And finally, maintenance, troubleshooting, and safety. Okay, so this entire process maps out into a really elegant 4-station blueprint: sample preparation, plasma atomization, signal detection, and finally data and maintenance. Now, understanding this physical journey from a raw, complex food sample walking into the lab all the way to generating highly accurate analytical data is the absolute secret to mastering your laboratory workflow. Every single station relies entirely on the success of the one right before it. Section 1. Breaking down the matrix. Preparing the sample. Every analysis begins with a fundamental decision tree, because an instrument can only analyze what we properly prepare for it. First off, you identify your matrix. Is it a simple, aqueous liquid, like wine, or a solid, like grain or tissue? If it's solid, well, it has to be broken down. But step 2 is where we really have to think ahead. Are volatile elements like arsenic, selenium, or mercury critical to your analysis? If the answer is yes, heating the sample in an open vessel will literally just boil away your analytes. We can't have that. So step 3 requires closed vessel microwave digestion. By operating at high pressure and temperatures up to 260 degrees Celsius, this destroys the organic food matrix while completely preventing any volatile loss. Now, listen carefully, because there is a severe hazard we need to talk about here. To digest silicates in certain samples, we use hydrofluoric acid, or HF. Unreacted HF is incredibly dangerous, and if left unchecked, it will literally dissolve the quartz and glass components of your sample introduction system. So the digestion must be neutralized with boric acid afterward. This step is absolutely non-negotiable. It converts the corrosive acid into harmless byproducts, protecting your expensive glass systems. Moving on to Section 2, igniting the plasma engine, atomizing the sample. I want you to think of the argon plasma as the literal engine of our system. First, high-purity argon gas flows through the torch. Next, a load coil applies a massive 1,000 to 1,500 watts of RF power, creating an intense electromagnetic field. Then, a high-voltage spark from a Tesla coil introduces seed electrons. This sparks a violently beautiful chain reaction, a cascade ionization process where electrons accelerate and collide with argon atoms. The result? A self-sustaining, brilliant plasma burning at an astonishing 6,000 to 10,000 Kelvin. To put that into perspective, that is hotter than the surface of the sun, generated right there on your benchtop. So, how do we harness this immense heat without melting everything? We use a specialized quartz torch made up of 3 concentric tubes. The outer tube carries a high flow of argon to shield the glass from melting. The intermediate tube lifts the plasma slightly up, but the inner tube, the injector, is where the real action happens. Its precise job is to plunge the fine sample aerosol directly into the absolute core of that 10,000 Kelvin plasma zone, instantly desolvating, vaporizing, and atomizing the sample. Section 3. Measuring light and mass. Signal detection. Now we get to the analytical magic. This is the fundamental difference between our 2 main technologies. They both use the exact same argon plasma engine we just talked about. The difference lies entirely in how they detect the signal. Think of it as eyes versus scales. ICP-OES acts as an optical eye. It measures the specific wavelengths of light, the photons, emitted as the excited analytes relax. ICP-MS, on the other hand, acts as a highly sensitive scale. It extracts the physical, singly charged positive ions right from the plasma using vacuum cones and literally sorts them by their mass-to-charge ratio. Eyes for light, scales for mass. So, in practical reality, when do you use each technology? Well, if you have a sample with a heavy matrix, meaning high total dissolved solids up to 20%, the robust ICP-OES is your best friend. It handles dirty samples beautifully and has moderate operating costs. However, if your target is highly regulated and requires extreme sub-part per trillion sensitivity, there is no choice. The ICP-MS is required. But keep in mind,
The MS has a very low tolerance for dissolved solids, only about 0.2%. It requires expensive cones, high vacuum pumps, and collision gases, which makes it much more costly to run.
Section 4. Calibration for precision. Trusting the data.
Remember, even the most powerful engine is completely useless if the dashboard gauges are lying to you. We have 3 main calibration strategies to ensure absolute precision. External standardization relies on a simple standard curve, which works great if your matrix is perfectly matched. Standard additions involves directly spiking the unknown sample, which is a lifesaver when matrix matching is impossible, but the absolutely crucial strategy here is the internal standard. For ICP-MS, adding a continuous online standard like scandium, yttrium, or bismuth is completely mandatory. Because the instrument's physical conditions can drift over time, this known standard acts as a constant baseline. It allows the system to mathematically correct for physical instrument drift and matrix suppression in real time.
Finally, Section 5. Maintenance, troubleshooting, and safety. Picture this scenario. You're in the lab. A critical batch of samples is loaded. You press ignition. The plasma sparks and then extinguishes immediately. The entire run is halted. What exactly causes this, and how do we fix it?
Actually, before we fix that dead plasma, let me share an insider pro tip for tricky elements. Sometimes elements like arsenic or selenium yield incredibly weak signals because they have a high ionization potential. Our secret weapon here is called a carbon boost. By adding just 1 to 2% isopropanol or methanol to the carrier solution, you trigger a charge transfer reaction in the plasma that massively boosts the ionization of these specific elements. It is a real game changer. Okay, returning to that extinguished plasma crisis. The diagnosis is almost always physical. It's typically a massive air leak in the O-rings, a blocked nebulizer, or most commonly a missing drain seal. The drain U-tube must be filled with liquid. That little loop of water creates a physical seal that prevents atmospheric air from rushing backward into the spray chamber and just blowing out the plasma. It is an incredibly simple check that saves hours of downtime.
To wrap things up, operating these instruments involves navigating intense radio frequency radiation, high-pressure gases, and deadly chemicals. Hydrofluoric acid, for instance, isn't just corrosive, it actually binds to calcium in human bones, making immediate access to calcium gluconate gel non-negotiable in the lab. These instruments hold immense power, allowing us to peer into the microscopic fabric of our world. But it's this very meticulous, often hazardous scientific process that happens behind closed laboratory doors to guarantee that the food matrix on our dinner tables is actually safe to consume. The next time you sit down for a meal, consider the 10,000-degree plasma that may have tested it.